Asteroids are the forgotten leftovers of our solar system's creation. We often picture them as just lonely, boring rocks drifting silently in the dark. But that picture is completely wrong. Today, we are going on a journey to uncover 25 truly bizarre and unexpected discoveries scientists have made on these cosmic wanderers. You will see that asteroids are not simple stones. They are dynamic, weird, and packed with mysteries that rewrite the story of our cosmic neighborhood. By the end, you will have a completely new understanding of what is really out there, from worlds made of solid metal to the hidden ingredients for life itself. How can a frozen rock spew jets like a comet? What does a diamond the size of a mountain floating in space actually mean? The answers will challenge everything you think you know. What is the strangest thing you believe could be hiding in the void? The first discovery shatters our driest expectations. We begin with water. For decades, the asteroid belt was seen as a cosmic desert, a place where the sun's heat had long since boiled away any volatile materials like water ice. These were just dry, baked stones. That assumption was proven spectacularly wrong. Using powerful telescopes equipped with spectrometers, which analyze the light bouncing off an object to reveal its chemical makeup, scientists pointed their instruments toward an asteroid named 24 Themis. The data returned a signature they never expected to see so deep in the inner solar system, the unmistakable fingerprint of water ice. This was not a one-time fluke. Further observations of the dwarf planet Ceres, the largest object in the asteroid belt, revealed not just hints of ice but bright, reflective patches in its shadowy craters, areas so cold that water ice can survive for eons. The shock comes from the environment. In the near vacuum of space, ice doesn't just melt, it sublimates, turning directly from a solid into a gas and vanishing into the void. Finding it means these asteroids are not simple, inert rocks. They are more like cosmic sponges or icy dirt balls, with water molecules likely trapped within their mineral structures or buried beneath a protective layer of dust that shields them from the sun's relentless glare. This changes everything about our own story. The leading theory for how Earth, a rocky planet formed close to the sun, got its vast oceans has always pointed the finger at incoming bodies from the cold outer solar system like comets. But what if the delivery drivers were much closer to home? Asteroids like Themis and Ceres present a compelling new possibility. They could have been the water carriers crashing into a young, hot Earth and depositing their frozen cargo, which then melted to fill our basins. It means the very ingredients for our blue planet, the cradle of all life, might have been lurking next door all along, hidden within what we thought were just barren stones. But water is only the beginning of the recipe. The next discovery adds something even more profound, the very chemical blueprints for life itself. On asteroids like Ryugu and Bennu, spacecraft have not just orbited these ancient rocks, they have touched down, collected precious grains of dust and brought them back home. When scientists in pristine, sterile laboratories finally cracked open those sample return capsules, they did not find just sterile rock, they found a treasure trove of organic molecules. These are not living things, but they're essential building blocks, complex carbon-based compounds like amino acids, which are the fundamental units of proteins and various hydrocarbons. Finding them is a staggering revelation. Space is an incredibly harsh place, bombarded by ultraviolet radiation from stars and cosmic rays that can shred complex molecules apart. The fact that these delicate organic compounds have survived for over 4 billion years, locked within the protective matrix of an asteroid, tells us they are not rare cosmic accidents. They are likely common, robust, and widespread. Think of these asteroids not as barren stones, but as ancient chemical arcs carrying a prebiotic cargo across the solar system. The implication is breathtaking. It means the basic ingredients for life, the very same kinds of molecules that eventually, under the right conditions on a young Earth, assembled into the first living cells, were being delivered right to our doorstep by countless rocky messengers. Life on our planet may not have had to start from absolute scratch. The starter kit, the fundamental chemistry, was raining down from the sky, embedded within these cosmic time capsules. This transforms our view of the universe's potential. If the ingredients are this common, then the possibility for life to emerge elsewhere, wherever similar conditions exist, becomes not just a hopeful dream, but a plausible, even likely, next chapter in the story of the cosmos. The building blocks for life are one thing, but asteroids can also harbor the remnants of celestial catastrophes on a scale we can barely comprehend. This brings us to a world that is not a rock at all, but a fragment of a cosmic skeleton. Deep within the asteroid belt orbits 16 Psyche, an object that defies every expectation. Based on its astonishing density and the way radar waves bounce off its surface with incredible brightness, scientists are convinced this is no ordinary asteroid. 16 Psyche appears to be a world of almost pure metal, a colossal sphere of iron and nickel over 200 kilometers wide. The leading theory is as dramatic as it sounds. This is the exposed, mangled core of a protoplanet that never was. In the violent early solar system, this embryonic world was likely stripped bare by colossal collisions. Its rocky mantle blasted away to leave behind only its metallic heart, cooling and solidifying in the endless dark. A mission is now on its way to visit this metallic relic, and what it might find sparks both scientific and economic fantasies. Imagine a landscape not of dust and stone, but of solid, unbroken iron, etched with canyons and cliffs forged in ancient impact. Its magnetic field, if one still exists from that primordial core, could be twisted into bizarre, invisible shapes, and within that metal, there could be loads of precious elements like gold, platinum, and rare earth metals in quantities that dwarf all the reserves on Earth. The sheer economic value is a dizzying, almost fictional concept, but the true treasure is scientific. 16 Psyche offers a one-way trip to a place we can never visit, the center of a rocky planet. By studying this exposed core, we are looking directly into the hidden engine of our own world, understanding the magnetic dynamo that protects Earth and the metallic heart that lies beneath our feet. It is a chance to read the diary of planetary formation written in elemental metal, a record of cosmic violence preserved for billions of years. The idea of a lone, drifting rock is another comforting illusion shattered by reality. Asteroids are not always solitary travelers. Many, in fact, come in pairs or even whole families. They form binary systems where a larger primary asteroid is locked in a gravitational dance with a smaller moonlet orbiting it like a planet orbits a star. One of the most famous examples is the Didymos system. Didymos itself is about 780 meters across, roughly the size of a skyscraper, and it is orbited by a much smaller moon named Dimorphos, which is only about 160 meters wide, no bigger than a great pyramid. How do these bizarre cosmic duos form? The leading theories are as violent as they are fascinating. A colossal impact on a single asteroid could blast off a huge chunk of debris that never fully escapes, instead getting caught in the gravitational pull of the main body, settling into a stable orbit as a new moon. Alternatively, if two asteroids pass too close to each other, their mutual gravity can, under just the right conditions, cause them to capture one another, becoming a bound pair drifting together through space. These systems are a navigator's nightmare and a scientist's dream. For a spacecraft aiming to visit or land on one, the complex gravity of two bodies creates a chaotic and unpredictable environment, a true orbital puzzle. But for researchers, that same complexity is a gift. By watching the moonlet's orbit, they can perform a cosmic weigh-in. The timing of its revolutions reveals the precise mass and density of the main asteroid, details that are incredibly difficult to measure from afar for a solitary rock. This brings us to a landmark moment, the Double Asteroid Redirection Test, or DART mission. In a historic first for planetary defense, humanity deliberately crashed a spacecraft into the moonlit Dimorphos. The goal was not destruction but deflection, a test to see if we could slightly alter the orbit of a small celestial body by transferring kinetic energy. The result was a spectacular success. The impact shortened Dimorphos' orbit around Didymos by a full 32 minutes, a change far greater than predicted, proving that we have the capability to nudge a potentially hazardous asteroid off course if we ever see one headed our way. That successful nudge also created a brilliant, expanding plume of dust and debris, revealing that Dimorphos is not a solid rock but a loose rubble pile, a revelation that came from the very act of trying to move it. So the next time you picture an asteroid, do not see a lonely stone. See a world with its own miniature moon, a delicate balance of rock and gravity holding a secret history of ancient impacts, and now a testament to our first steps in learning how to protect our own world from them. The rubble pile nature of Dimorphos reveals another truth about these bodies. They are fragile, dynamic, and sometimes astonishingly active. This leads us to a category of object that defies all simple classification, the active asteroids. Forget the quiet, stoic rocks. Picture instead an object like 3,200 Phaethon. This is a sizable asteroid, over 5 kilometers across, and it follows an orbit that swings it scorchingly close to the Sun, closer than Mercury. For years, it was just another dot in the catalogues. Then, telescopes caught it in the act. As Phaethon neared its perihelion, its closest approach to the Sun, something extraordinary happened. It began to brighten dramatically, and a faint but unmistakable tail of dust streamed out behind it, just like a comet. But here is the crucial, baffling detail. Comets develop their glorious tails when their subsurface ices heat up, vaporizing into gas and dragging dust with them into space. Phaethon's orbit brings it so close to the Sun that its surface temperature soars to over 700 degrees Celsius, hot enough to melt lead. Any trace of water ice should have been baked away eons ago. So what is creating this tail? The leading suspect is a process called thermal fracturing. Think of a stone in a campfire. The intense, uneven heat causes the rock to expand and crack, sometimes violently. On Phaethon, the solar heating is so extreme it may be literally blasting the surface apart, popping off dust and rubble through sheer thermal stress. Another active asteroid, 133P/Elst Pizarro, adds another twist. It resides in the main asteroid belt, and yet periodically it too sprouts a dusty tail. Its activity might be driven by a different engine, perhaps the subtle buildup of pressure from hidden reservoirs of ice finally finding a weak spot to vent, or even the centrifugal force from the asteroid spinning so fast it flings material from its equator. These active asteroids live in a blurry, confusing borderland. They have the rocky composition and typical orbits of asteroids, but they display the volatile behavior of comets. This forces us to abandon our neat little boxes. The solar system is not a museum with separate shelves for rocks and ice balls. It is a continuum, a spectrum of worlds where processes we are only beginning to understand can make a dry, sun-baked stone cough dust into the void. The visual proof is in the telescope images, where a point of light that should be inert is caught with a faint, ghostly smear stretching away from it, a silent testament to the hidden forces still at work on these ancient nomads. If a rock can behave like a comet, what other cosmic identities have we been getting wrong? The ghostly tales of active asteroids hint at a deeper truth about their fundamental nature, a truth that is both bizarre and counterintuitive. Many of these worlds are not solid, monolithic stones at all. They are cosmic jigsaw puzzles that were never glued together, known to scientists as rubble piles. Imagine a mountain in space, but a mountain made not of bedrock, but of a trillion loose boulders, rocks, and fine dust, all gently held in a tenuous embrace by their own minuscule gravity. This is the true structure of asteroids like Bennu and Ryugu, as revealed in stunning detail by the spacecraft that visited them. When the OSIRIS-REx probe descended to collect a sample from Bennu, its touch-and-go maneuver did not land on a firm surface. It was more like dipping a cup into a gravel pit. The spacecraft's thrusters blasted away the top layer with shocking ease, sending a chaotic plume of debris flying into the void, and its sampling arms sank in much deeper than anticipated, revealing a world with virtually no structural integrity. The data confirmed it. These asteroids are mostly empty space with porosities over 50%, meaning more than half of their volume is just gaps between the rocks. They are less like mountains and more like floating, self-contained heaps of celestial debris. This fragile architecture rewrites their entire history. A rubble pile is likely the reassembled corpse of a much larger parent body that was utterly shattered in a cataclysmic collision billions of years ago. The fragments, unable to escape each other's weak gravity, slowly, gently coalesced back into a new but profoundly fragile aggregate. This has dramatic consequences. When another small meteorite strikes a rubble pile, it doesn't create a classic crater. Instead, the impact energy is absorbed by the entire structure, shaking it like a bag of marbles and simply rearranging the surface material. The asteroid literally gives way, absorbing the blow without a scar. This also makes them incredibly responsive to external forces, like the gentle pressure of sunlight, which can slowly alter their rotation and even their trajectory over time. So, the next time you look at an image of a diamond-shaped asteroid like Ryugu, do not see a solid rock. See a delicate, spinning mosaic of ancient wreckage, a world where you could kick the surface and start an avalanche, a testament to the gentle, persistent force of gravity that can, against all odds, hold chaos together in the shape of a world. The delicate, porous nature of a rubble pile has a direct and visible consequence. It allows asteroids to take on forms that defy any logic born of solid ground. Gravity here is not a powerful sculptor, but a faint suggestion, and that permits a gallery of cosmic oddities. Look at asteroid 216 Cleopatra, captured in stunning detail by ground-based radar. This is not a sphere, not even a lumpy potato. It resembles a giant dog bone or perhaps a cosmic barbell with two distinct lobes connected by a thick, slender neck. This bizarre shape is the product of a wild, chaotic dance. Cleopatra spins so rapidly, completing a full rotation in about 5 hours, that its own weak gravity cannot pull it into a rounded shape. Instead, the centrifugal force flings material outward at its equator, while the poles collapse inward, stretching and deforming the entire body into this surreal, elongated form. It is a shape that could not exist on a world with substantial gravity, a testament to the strange physics of the vacuum. Then there is the now familiar Ryugu, with its distinct spinning top or diamond-like appearance. This shape is also a signature of rapid rotation, where loose surface material naturally migrates toward the equator, piling up to form a pronounced, sharp ridge that girdles the entire middle of the asteroid. These are not static sculptures, they are dynamic, frozen moments in an ongoing process, where the slightest nudge from another impact or the gentle push of sunlight could, over millions of years, reshape them again. Their surfaces tell an equally dramatic story. Without strong gravity to pull debris down slopes, the landscape becomes a frozen record of violence and chance. Enormous boulders, some the size of houses or even small hills, litter the surfaces of Bennu and Ryugu. These are not native to the spot, they are ejecta from ancient, colossal impacts on the parent body, now resting precariously on a surface with barely any pull. How does a boulder the size of a cathedral come to rest on a world where a person could jump off into space? It simply landed there and stayed because nothing has come along to move it. Equatorial ridges like the one on Ryugu act as cosmic conveyor belts, slowly channeling material around the midsection. And then there are the mysterious bright spots, most famously on the dwarf planet series. The brilliant patches within Arcata crater gleam with the reflectivity of fresh salt deposits, likely left behind when briny water erupted from a subsurface reservoir in a fleeting cryovolcanic event and then sublimated away, leaving only the bright residue behind. Each of these features, from the dog bone shape to the lonely boulder, is a clue. The shape reveals the asteroid's spin history and internal weakness. The presence of giant, unburied boulders confirms its rubble pile nature and violent past. Bright spots betray hidden, volatile activity. To understand an asteroid, you must learn to read this alien topography, a language written not in rock, but in gravity's absence and the relentless patience of time. Visualizing these worlds requires a shift from thinking in photographs to thinking in motion. Imagine a 3D model of Cleopatra tumbling end over end in the blackness, its strange silhouette casting a shifting shadow, or Ryugu spinning like a wobbly top, its equatorial ridge standing proud against the stars. These are not mere rocks, they are sculptures in a zero-gravity gallery, each one a unique masterpiece of celestial mechanics. These delicate shapes and surface features are a testament to an asteroid's external life. But to uncover its internal history, we must look at the clues locked within the rocks themselves, clues that point to a surprisingly dynamic past. Some of the most compelling evidence doesn't come from telescopes or spacecraft, but from stones that have fallen to Earth. When scientists examine certain meteorites, known to have originated from the crust of differentiated asteroids, they make a startling discovery embedded within the rock's very crystals. These meteorites contain a faint but measurable record of an ancient magnetic field. It is a fossil magnetism, a ghostly signature preserved in the alignment of tiny iron-rich minerals that cooled and locked into place billions of years ago, pointing like a compass needle to a field that has long since vanished. The implication is profound. For a rocky body to generate a global magnetic field, it needs a churning, molten metallic core, a dynamo in motion. We see this active process today in planets like Earth. But an asteroid is tiny, often just a few hundred kilometers across or less. Its interior should cool and solidify rapidly in just a few million years, snuffing out any magnetic dynamo almost instantly after formation. Finding this magnetic record is like finding the fossilized heartbeat of a mouse, a pulse that by all rights should never have existed. So how do these small worlds briefly come alive with magnetic energy? The leading theories point to episodes of intense, catastrophic heating. One possibility involves short-lived radioactive isotopes like aluminum-26, which were abundant in the early solar system. As these hot atoms decayed, they could have provided a powerful, if brief, internal furnace, melting the asteroid's metal and allowing a dynamo to churn for a few million glorious years before the fuel ran out and the core froze forever. Another, more violent explanation involves colossal impacts. A giant collision could have delivered so much energy that it partially remelted the asteroid's interior, restarting its metallic heart for one final, fleeting magnetic spasm. This transforms our view of these small bodies. They were not always the cold, dead rocks we see today. In their youth, some were miniature worlds with liquid, swirling cores, generating protective magnetic bubbles in the solar wind. They had inner fire and dynamism. To visualize this, picture a cut open meteorite in a lab, its polished face revealing beautiful, intricate patterns. Within those patterns, invisible to the eye, are minerals aligned to a north pole that no longer exists. Or imagine an artist's depiction of that ancient asteroid, its stony crust hiding a glowing sphere of molten iron and nickel, with magnetic field lines arcing out into space like the invisible shield of a planet. This fossil magnetism is a whisper from the dawn of the solar system, a direct measurement of the thermal and violent childhood of worlds that never grew up, reminding us that even the smallest fragments of our cosmic neighborhood once held the fire and force of a planet. The ghost of a magnetic field is a whisper from an ancient past, but some visitors bring mysteries that are happening right now. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted an object moving at impossible speeds. It was not orbiting the sun, it was passing through, a lone traveler from another star system. They named it Oumuamua, a Hawaiian word meaning scout from the distant past. This was our first confirmed interstellar visitor, and its characteristics were utterly bizarre. First was its shape. Based on how its brightness fluctuated dramatically as it tumbled, scientists deduced it was profoundly elongated, perhaps 10 times longer than it was wide. Think of a cigar, or more likely, a flat pancake tumbling end over end through the void. No asteroid or comet in our solar system has such an extreme form. Then came the real puzzle, its motion. As it raced away from the sun, tracking data revealed it was accelerating slightly, deviating from a path dictated by gravity alone. Comets do this all the time through outgassing, when sunlight vaporizes their ices, and the jetting gas acts like a tiny rocket engine. But Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that surrounds an active comet. It appeared as a dry, inert point of light, so what was pushing it? The scientific debate exploded. Some proposed exotic natural explanations, like it being a chunk of solid hydrogen ice. As it neared the sun, the hydrogen would sublimate furiously, providing thrust without leaving a dusty trail we could see. Others suggested it was a dusty fractal, an incredibly lightweight aggregate of material that sunlight itself could push, like a cosmic sail made of rubble. The lack of a clear answer opened the door to more speculative ideas, including the tantalizing, though highly unlikely, possibility of artificial origin. The sober truth is that Oumuamua's brief visit was a masterclass in cosmic humility. It presented us with a genuine anomaly, a set of data that did not fit neatly into any existing category. We had one chance to observe it, and then it was gone forever, back into the interstellar dark. Its legacy is not an answer, but a profound question. It reminds us that the universe is capable of crafting objects beyond our current imagination, shaped by physics and chemistry in alien star systems we may never see. Artist impressions try to capture its strangeness, showing a reddish, slab-like object tumbling chaotically against the backdrop of stars, a silent messenger that challenged our textbooks and left us wondering what else is sailing the vast ocean between the stars, unseen and unexplained. The strangeness of interstellar visitors like Oumuamua forces us to look closer at the familiar, and there we find another slow-motion mystery unfolding right before our eyes. Asteroids are changing color. If you could watch one for 1,000,000 years, you would see its surface gradually darken and take on a reddish tint, a process scientists call space weathering. It is the cosmic equivalent of a suntan, but far more violent. The surface of an asteroid is naked to the void, constantly bombarded by two invisible forces. The first is the solar wind, a relentless stream of charged particles blasted from the sun at over 1,000,000 miles per hour. These tiny particles smash into the mineral grains on the surface, damaging their crystalline structure. The second is a constant drizzle of micrometeorites, dust-sized fragments traveling at phenomenal speeds that act like microscopic sandblasters. Together, this bombardment has a transformative effect. Think of a fresh fracture on a rocky cliff face. It is bright and reflective. On an asteroid, that fresh material is exposed when a new impact blasts away the old surface. But over time, the solar wind and micrometeorites work on it. They vaporize tiny amounts of iron present in the minerals, and that iron then condenses into nanoscale particles that coat the surrounding grains like a fine, dark dust. This process darkens the surface and gives it a reddish hue because those tiny iron particles scatter red light more efficiently. The surprise for scientists was seeing just how varied this aging process can be. By comparing asteroids of different types and in different locations, they can essentially see a gallery of cosmic aging. Some, like the asteroid Itokawa, visited by the Hayabusa spacecraft, show a classic, uniformly weathered surface, a dull grayish red that speaks of eons of exposure. But then you have the baffling exceptions. Certain asteroids, or even patches on asteroids, appear shockingly bright and blue, almost as if their surfaces were freshly scrubbed. How is that possible? The leading explanation points to recent violent events. A sizable impact could have occurred just a few 100,000 years ago, a blink of an eye in cosmic terms, excavating pristine material from deep below the weathered crust and scattering it across the surface before the darkening process had time to take hold. Alternatively, on a fragile rubble pile asteroid, seismic shaking from a distant impact could cause a global landslide, literally turning the world over and exposing fresh, unweathered interior material. This transforms asteroids from static museum pieces into dynamic, aging worlds with their own life cycles. To visualize it, imagine a time lapse spanning 1,000,000 years. Watch as a brilliant white crater slowly fades to gray, then to a deep, ruddy brown, its sharp edges softening under an invisible rain. Or place two images side by side, one of a dark, reddened asteroid that has been sitting in the solar wind's path for billions of years, and another of a brilliant, blue-tinged fragment that just recently tumbled into view. That color is a clock, a testament to how long a surface has been facing the sun and the stars, a silent record written in light and shadow. The silent clock of space weathering points to a surface constantly reshaped by violence, but to witness the full scale of that violence, we must zoom out from a single rock to view an entire family. Asteroids are not just individuals, they are survivors of ancient dynasties, born from single, catastrophic events. Scientists can trace these lineages through cosmic forensics, grouping together asteroids that share remarkably similar orbits and spectral signatures, meaning their surface composition is virtually identical. These are known as asteroid families, and they are the direct descendants of a titanic collision that shattered a single, larger parent body hundreds of millions or even billions of years ago. The debris from that primordial smash-up, all moving with similar speed and direction, slowly spread out along the parent's original orbital path, creating a clan of fragments that still travel together through space. One of the most dramatic and well-studied examples centers on the giant asteroid 4 Vesta. Vesta is a protoplanet, a surviving embryo from the solar system's formation, and its southern hemisphere is dominated by a staggering impact basin called Resilvia. This crater is so enormous it covers almost the entire South Pole, with a central peak that rivals the height of Mount Everest. The impact that carved Resilvia was of almost unimaginable force, likely occurring around 1 billion years ago. It blasted an estimated 1% of Vesta's entire volume into space. Today, we can trace the scattered children of that event. A whole family of smaller asteroids, known as the Vestoids, share Vesta's unique mineralogical fingerprint, and they follow orbits that clearly point back to their origin point. Even more incredible, some of that debris didn't stay in the belt. Through complex gravitational nudges, pieces were eventually sent on a collision course with Earth. We have held these fragments in our hands. A significant percentage of all meteorites found on our planet, known as HED meteorites for howardite, eucrit, and diogenite, are confirmed to be pieces of Vesta's crust and mantle, blasted across the solar system that long ago. Studying an asteroid family is like arriving at the scene of a cosmic car crash billions of years after it happened. The vehicles are gone, but by meticulously mapping the position, speed, and makeup of every piece of debris still floating in the road, you can reconstruct the size of the original objects, the angle of the impact, and even the terrifying energy released. Visualize a dynamic animation starting with a serene, fully formed protoplanet. Then, a shadow falls as another massive body, perhaps dozens of kilometers across, screams in from the void. The impact is not a simple explosion, it is a world-ending event. The shockwave rips through Vesta's crust, launching plumes of molten and solid rock into space in a slow-motion fountain of destruction. The camera pulls back to show the resulting cloud of fragments, thousands of them, slowly drifting apart along the old orbital highway, a permanent testament to the day a world was nearly destroyed. This forensic work reveals the asteroid belt not as a quiet graveyard, but as an active crime scene where the evidence of ancient, planet-shattering violence is still written in the paths of the stones. The forensic evidence of ancient collisions leads us to a deeper chemical mystery, locked within the very minerals that make up these rocks. While we might expect asteroids to be composed of common, boring stone, the reality is a dazzling array of unexpected crystals, each one a time capsule from the solar system's birth. On Earth, minerals form under specific conditions of pressure, temperature, and chemistry. Finding a particular mineral is like finding a fossilized recipe, telling you exactly what the kitchen was like when it was made. This is why the minerals discovered on asteroids have delivered such profound shocks. Take the asteroid 4 Vesta. Spectroscopic data and meteorites confirmed it is rich in olivine and pyroxene. That might sound like geological jargon, but think of it this way. Olivine is the beautiful green gemstone peridot, and it typically forms in the mantle of a rocky planet, deep under immense pressure. Finding it on Vesta's surface means we are looking at a world that differentiated, that melted and separated into a core, mantle, and crust. Vesta literally turned itself inside out through ancient volcanism, bringing its deep interior material to the surface where we can see it. This alone was a revelation for such a small body, but the surprises grew stranger. Some meteorites, believed to be from other, more primitive asteroids, contain minerals that should not exist in the cold, dry vacuum of space. They are minerals like clays and various hydrated salts, which can only form in the presence of liquid water. How does a water-bearing mineral end up on a tiny, airless rock that has never been warm enough to host a lake or an ocean? The answer points to a far more dynamic and wet early solar system. These minerals are likely primordial. They formed when the asteroid itself was coalescing from the dusty disk around the infant sun, incorporating ice that later melted, perhaps from the heat of radioactive decay, allowing brief episodes of liquid water to percolate through the rock and alter its chemistry before refreezing for eternity. Even more perplexing are traces of minerals that typically require immense pressure to form, the kind of pressure found only deep within a planet. Their presence hints that these asteroids or their parent bodies experienced unimaginably violent collisions, generating transient, planet-like pressures in the shock of impact, forging exotic crystals in an instant before the debris flew apart. To see this evidence is to look at art. Scientists slice meteorites into sections thinner than a human hair and place them under polarized light microscopes. The resulting images are not gray and dull. They are explosions of color, swirling mosaics of pinks, blues, and radiant yellows, each hue representing a different mineral with a different story. That vibrant tapestry is a direct map to the past, a chemical fingerprint of the pressure, heat, and even the fleeting presence of water that existed over 4 billion years ago. Every unexpected crystal is a clue, forcing us to redraw the map of the asteroid belt not as a simple, dry construction zone, but as a complex chemical laboratory where recipes for planets were tested, altered, and sometimes frozen in time. These vibrant mineral maps reveal the solar system's chemical diversity, but they only tell half the story. Some asteroids hide their nature in absolute shadow. Among the darkest objects known to science are the mysterious D-type asteroids, a class so dim they nearly vanish against the void. Take 152 Atala, a resident of the outer asteroid belt. Its surface reflects less than 5% of the sunlight that hits it, an albedo lower than fresh asphalt. To understand why, we must look at its coating. These worlds are not made of bare rock or metal. They are shrouded in a complex, tar-like sludge of organic compounds known as tholins. This material forms when simple molecules like methane or nitrogen, bombarded by ultraviolet radiation from the sun or cosmic rays, link together into long, complex chains of carbon. The process is a slow, cosmic chemistry experiment played out over billions of years on a frozen stage. The resulting tholins are dark, sticky, and rich in carbon, giving these asteroids their profound blackness and a deep reddish tint. Their significance is monumental. While most asteroids in the inner belt have been baked and battered by the sun, D-types like Atolla are thought to be primitive refugees. They likely formed much farther out, in the cold, dark realms beyond Jupiter, perhaps even in the Kuiper belt where Pluto resides, and were later scattered inward by gravitational interactions. This means their surfaces have never been heated enough to evaporate those fragile organic tars. They are cosmic time capsules, preserving some of the most ancient and unaltered chemistry from the solar system's birth, a chemistry that may be very similar to the nuclei of comets. Visualizing this contrast is striking. Imagine a side-by-side comparison. On one side, a bright S-type asteroid like Vesta, reflecting 30% of the sun's light, gleaming like a dirty snowball against the black. On the other, a D-type like Atolla, a featureless black silhouette that drinks the light, its outline only discernible as it blots out the stars behind it. To land on such a world would be to step into an abyss where the ground underfoot is a frozen primordial tar pit, a snapshot of the cosmic ingredients that existed before the planets were even born. These dark wanderers are not merely oddities, they are shadows of the distant past, drifting silently in from the cold outer dark to remind us how much of our history is still painted in the deepest black. The profound darkness of a D-type asteroid speaks of ancient stillness, but on other worlds, the surface is anything but still. Look closely at the high-resolution images sent back by orbiting spacecraft, and you will see the scars of recent violent motion. On the asteroid 433 Eros, a world shaped like a cosmic peanut, scientists examining photographs from the near Shoemaker mission spotted something strange. Long, linear tracks snaked across the dusty plains, as if giant boulders had been dragged across the terrain. On Bennu, the OSIRIS-REx orbiter captured even clearer evidence, fresh, bright landslide scars on crater walls, with piles of debris slumped at the bottom and boulder trails that looked startlingly new. These are not ancient features weathered by eons of space. They are the equivalent of fresh mudslides on a mountain road, evidence that the surface of an asteroid is actively, and sometimes dramatically, changing. The force behind this reshaping is not wind or water, it is the asteroid itself trembling. Scientists call these events asteroid quakes. In the microgravity of a small world, even a tiny tremor can have monumental consequences. A single boulder perched precariously on a slope might need only the slightest nudge, a vibration no stronger than a gentle hum, to break free and begin a slow, majestic tumble down a crater wall, carving a crisp track in the fine regolith as it goes. But what could possibly cause a quake on a lonely rock in space? The sources are as varied as they are relentless. The most obvious is impact. Even a small meteorite, no larger than a pebble, striking the surface at tens of thousands of miles per hour, sends a seismic shockwave rattling through the fragile rubble pile interior, shaking the entire world like a bell. Another, more subtle driver is thermal stress. As an asteroid rotates, its surface experiences extreme temperature swings, from blistering heat in direct sunlight to deep cold in shadow. This constant expansion and contraction of the rock itself creates stress that can build up and suddenly release, fracturing boulders and triggering slides. Finally, for rapidly spinning asteroids, centrifugal force itself can be the culprit. If the rotation is fast enough, it can literally cause the world to start flying apart, with material at the equator becoming unstable and cascading down toward the poles in global-scale avalanches. The visual proof is in the before and after images. Orbiters have captured the same patch of terrain months or years apart, and in that short cosmic interval, new slide marks appear, fresh debris piles form, and boulder tracks that weren't there before now etch the gray landscape. This transforms our understanding completely. Asteroids are not inert, dead museums. They are seismically active worlds, their surfaces constantly being remodeled in an achingly slow, silent ballet of shifting dust and stone, all driven by the gentle, persistent forces of a sunlit vacuum. Those shifting, dusty surfaces hide a secret of unimaginable hardness. Deep within the structure of some asteroids, carbon atoms have been forced into the most indestructible arrangement known, creating diamonds in the sky. This is not science fiction or wishful thinking. It is a conclusion drawn from the rocks that have fallen to our planet. A rare class of meteorites called uralites tells a violent and glittering story. When scientists analyze these dark, carbon-rich stones, they find something extraordinary embedded within the matrix, tiny crystals of diamond. These are not the kind you would find in a jewelry store. They are microscopic, often just nanometers across, but they are real diamonds forged in the heart of cosmic chaos. How does a gemstone that requires immense pressure to form end up inside a small, airless asteroid? The answer points to a moment of apocalyptic force. The leading theory suggests that when two sizable protoplanets collided in the early solar system, the shock wave from that impact sent a pressure wave of almost inconceivable intensity through the carbon-rich material. In an instant under that transient, planet-like pressure, the carbon atoms were crushed into the rigid, tetrahedral lattice of diamond. It is a process akin to creating a synthetic diamond in a lab with a massive press, but on a cosmic scale, with the entire universe providing the hammer. While we are not talking about literal planet-sized gemstones waiting to be mined, the implications are profound. The presence of diamond, and its more common cousin graphite, reveals that asteroids can be treasure chests of exotic, high-value materials formed through the most extreme events. Imagine a visualization of an asteroid's interior, not as uniform rock but as a complex matrix. Within that gray bulk, highlighted in brilliant, schematic lines, are countless microscopic diamond crystals, each one a frozen testament to a collision that reshaped worlds. This transforms our understanding of value in the cosmos. An asteroid is not just a lump of iron or ice. It can be a museum of mineralogical extremes, carrying within it the shattered remnants of a pressure event so violent it turned cosmic soot into one of the hardest substances in existence. What other impossible materials might be locked within these wandering stones, forged in the furnace of creation's most violent moments? The diamonds forged in ancient collisions speak of pressure, but another discovery reveals a process of release so delicate it is almost a whisper. Some asteroids, against all logic, can briefly hold onto an atmosphere, not the thick, swirling skies of a planet, but an exosphere, an impossibly thin envelope of gas so tenuous that the individual molecules within it rarely ever collide. The dwarf planet series provides the most stunning example. Observations from orbiting spacecraft have detected definitive plumes of water vapor rising from its surface, particularly from those brilliant, reflective patches within Okata crater. The source is likely a buried reservoir of briny ice, heated by the residual warmth from the impact that created the crater itself or by internal activity. This subsurface slush occasionally finds a weak spot in the crust and vents into the vacuum, the water vapor instantly freezing into a fine mist of ice crystals or escaping as a transient, localized atmosphere before the cold and vacuum reclaim it. Even smaller, more traditional asteroids can achieve this fleeting state. As a rocky body on a highly elliptical orbit swings close to the Sun, the intense heat can bake out gases that have been trapped for eons within its mineral matrix or absorbed onto dust grains. For a short time, the asteroid is surrounded by a cloud of its own released breath, atoms of sodium, potassium, or even argon slowly leaking away into space. This phenomenon utterly blurs our cosmic categories. We are taught that planets have atmospheres and asteroids do not. Yet here is a world like Ceres, a resident of the asteroid belt, actively venting its own vapors, and a smaller rock briefly shrouding itself in a gaseous halo. It is a temporary state of being, a glimpse of what might have been if these objects had been more massive, able to hold onto their volatile gases permanently. To visualize this, imagine an animation of a lumpy, gray asteroid approaching a brilliant, flaring sun. As solar radiation bathes its surface, faint, shimmering streams of atoms begin to rise from the hot side, like heat haze off a desert road, creating a faint, shimmering cocoon that stretches out behind it in its orbital path before fading back into the black. It is a ghost of an atmosphere, a memory of gas that highlights the dynamic, changing nature of even the smallest worlds, constantly losing themselves molecule by molecule to the endless night. The ghostly atmosphere of a venting asteroid is a silent process, but sometimes the universe delivers its messages with thunder. The morning of June 30th, 1908, in a remote part of Siberia, a fireball brighter than the sun tore across the sky. Moments later, a shockwave of unimaginable force flattened 80 million trees across 800 square miles of forest, an area larger than a major city. This was the Tunguska event, and for over a century, its cause remained one of the planet's most compelling cosmic mysteries. The effects were as bizarre as they were terrifying. Witnesses hundreds of kilometers away were thrown from their chairs by the blast, their clothes feeling searingly hot. Seismographs across Europe and Asia recorded the ground shaking as if from a major earthquake, and barometers detected atmospheric pressure waves that traveled around the globe not once but twice. In the nights that followed, skies from London to Moscow glowed with an eerie, silvery light, so bright that people could read newspapers at midnight. This celestial light show was caused by vast amounts of dust from the explosion lingering high in the atmosphere, scattering sunlight across the hemisphere. The most perplexing clue, however, was what scientists did not find when they finally reached the remote site decades later. There was no crater. The epicenter showed scorched, stripped trees standing upright like telegraph poles, with the devastation radiating outward in a vast butterfly pattern. This absence provided the crucial answer. The object, likely a stony asteroid or a fragile comet fragment roughly 60 meters across, never struck the Earth. It exploded in a massive airburst about 5 to 10 kilometers above the ground, the pressure and heat of its hypersonic entry causing it to disintegrate catastrophically in a flash of energy equivalent to 10 to 15 million tons of TNT. The blast was a purely atmospheric event, a hammer blow of superheated air that did all the damage. Tunguska reshaped our understanding of planetary threat. It proved that we do not need a direct impact from a mountain-sized object to face a regional catastrophe. A relatively small, common asteroid, one that would be incredibly difficult to detect until it was very close, could unleash the destructive power of a large thermonuclear weapon simply by exploding in our sky. It is a stark and humbling reminder that asteroids leave their mark not only with craters, but with the very air we breathe turned into a weapon. Historical photographs of the Tunguska site are haunting, showing endless square miles of trees laid flat like matchsticks, all pointing radially away from that silent, invisible point in the sky where a visitor from the deep cosmos announced its arrival with a flash and a roar that echoed around the world. The roar of Tunguska was an instant of violence, but on some asteroids the fire burned for millions of years, reshaping them from within. The evidence for this lies on the giant asteroid 4 Vesta, a world that dared to become a planet. When the Dawn spacecraft arrived, its cameras revealed a landscape that should not exist. Instead of a uniform, cratered crust, Vesta's surface was a complex mosaic, with vast, smooth plains that looked suspiciously like frozen floods. These are not impact melts, they are the unmistakable signatures of ancient basaltic lava flows. This means Vesta, a body only 525 kilometers across, did something extraordinary. It differentiated. In its youth, its interior grew so hot that it completely melted, allowing heavy metals like iron and nickel to sink to the center, forming a dense core, while lighter, silicate-rich magma rose to the surface and erupted through volcanoes, spreading out in liquid sheets that later cooled into the dark basaltic plains we see today. The very existence of these flows is a profound puzzle. How could something so relatively small generate that much internal fire? Planets like Earth retain their inner heat due to their immense size, but an object like Vesta should have cooled and solidified within a few million years, a cosmic blink. The answer is a primordial furnace. In the chaotic first few million years of the solar system, the building blocks of planets were laced with short-lived radioactive isotopes like aluminum-26. This material was intensely hot, acting like a network of microscopic coals scattered through the asteroid's body. As these radioactive atoms decayed, they released a tremendous, sustained heat that was trapped inside Vesta's growing bulk, cooking it from the inside out until the entire world was a churning, molten sphere. This process transformed Vesta from a simple lump of rock and metal into a layered, complex protoplanet with a core, a mantle, and a volcanic crust. To visualize this, picture a topographic map of Vesta's surface. The southern hemisphere is dominated by the colossal Resilvia impact basin, a scar of unimaginable violence, but in the northern regions you would see those vast, smooth expanses, their boundaries flowing around older craters and topography like hardened syrup. An artist's depiction might show Vesta in its fiery youth, its surface cracked open in great fissures, fountaining incandescent lava under a black sky, a miniature world alive with its own geological heartbeat. This evidence rewrites the story of small bodies. They were not always cold and dead, some were once dynamic volcanic worlds, their surfaces shaped not just by impacts from without, but by fire from within. If an asteroid can have volcanoes, what other planetary secrets do these small worlds hold? That inner fire within Vesta points to an even grander, more tragic narrative. The bizarre collection of objects we find in the asteroid belt, from metallic cores to volcanic crusts and water-rich rubble, may all be characters in the same story. They are likely the scattered remains of not just one, but many lost worlds, protoplanets that were never allowed to grow up. The leading theory paints a dramatic picture of the early solar system. As dust and gas swirled around the young sun, countless smaller bodies called planetesimals began to stick together through collisions, a process of cosmic snowballing that should have formed several rocky planets between Mars and Jupiter. But a titan was stirring. Jupiter, the solar system's giant, was forming nearby, and its immense gravitational pull acted like a cosmic wrecking ball. As these infant protoplanets or planetary embryos grew, Jupiter's gravity stirred their orbits into chaos. Instead of gently merging, they were flung into violent, high-speed collisions. The impacts were not constructive but utterly destructive, shattering these nearly formed worlds back into fragments. Some were completely pulverized, their debris scattered across the inner solar system. Others, like Vesta, survived as battered, incomplete relics. This explains the incredible diversity we see. The metallic asteroid Psyche is the iron heart of one of these destroyed embryos stripped bare. Vesta is the scorched volcanic crust and mantle of another. The carbon-rich, dark D-type asteroids are the primitive, unaltered building blocks that never got incorporated. The water-bearing minerals and clays are the chemical remnants of brief, warm periods inside these small worlds before they were blasted apart. Every bizarre discovery fits into this epic, billion-year-old crime scene. To visualize this is to watch the birth and death of planets. Imagine an animation of the early solar system, a bustling construction zone. Dozens of glowing, molten protoplanets, each with a differentiated core and mantle, orbit in a busy disk. Then, the gravitational influence of a massive, growing Jupiter, represented by swirling waves of distortion, destabilizes their paths. The scene becomes one of celestial carnage. Two embryonic worlds, one metallic-rich, one water-rich, hurtle toward each other. The collision is not a clean merger, but a blinding flash of light and a catastrophic spray of debris. The metallic core of one is sent spinning away, a naked, cooling sphere. The crust and mantle of the other are shattered into a million fragments, some rocky, some carrying the chemical memory of water. Over eons, Jupiter's gravity continues to shepherd this debris field, preventing it from reassembling, condemning it to remain a belt of fragments, a graveyard of planetary potential. This grand perspective ties every strange piece together. We are not just looking at random rocks, we are cataloging the fossilized anatomy of stillborn planets, collecting the scattered pages of a story that was interrupted before it could truly begin. These shattered remnants of lost worlds are not just isolated tombstones, they are active curators, collecting artifacts from across the cosmos. The next discovery reveals that asteroids are cosmic sponges, soaking up and preserving material from other solar system bodies entirely. This evidence comes from the most pristine samples we have ever collected, the grains of dust returned from asteroids like Ryugu and Bennu. When scientists placed these specks under powerful electron microscopes, they saw more than just the asteroid's own material. They found tiny, exotic grains with chemical signatures that did not match the host rock at all. Some of these microscopic hitchhikers carried the unmistakable fingerprint of Vesta, the protoplanet from the main asteroid belt. Others were even more alien, identified as tiny specks of interstellar dust, grains that formed around other stars long before our own sun was born and were later captured as our solar system swept through the local galactic cloud. This is contamination on a cosmic scale, and it tells a profound story of connection. An asteroid spends billions of years on its lonely orbit, but it is not traveling through a perfect vacuum. The space between planets is filled with a fine, invisible mist of dust, the debris from comets, the ejecta from distant impacts, and even material from beyond our solar system. As the asteroid moves, this dust rains down upon its surface at tremendous speeds, and some of it embeds itself, becoming trapped in the soft, porous regolith like a fly in amber. Over eons, the surface of an asteroid becomes a layered archive, a museum of extraterrestrial artifacts. Each microscopic grain is a time capsule from a different event and a different location. Finding a piece of Vesta on Bennu is like finding a shard of Roman pottery in an Egyptian tomb, evidence of ancient trade routes or, in this case, ancient collisions that sent material flying across vast stretches of the solar system. The interstellar grains are even more staggering. They are literal stardust older than our entire planetary system, delivered to a rocky outpost for safekeeping. To see this evidence, picture a false color microscope image. The background is the gray, lumpy matrix of the asteroid itself, but scattered within it, highlighted in brilliant blues and reds, are these perfect crystalline grains, their alien chemistry revealed by the scan. They look like tiny gems sewn into a rough fabric. This transforms our understanding of an asteroid's role. They are not just relics of their own formation, they are active collectors, silent archivists gathering the scattered history of everything around them. By studying one asteroid, we are not just learning about one world, we are sampling the entire neighborhood and even the galaxy beyond. What other lost chapters of cosmic history might be waiting, embedded in the dust of these wandering stones? The microscopic archives of an asteroid reveal its surface history, but to understand its true nature, we must peer into its heart. There we find a paradox, an object that seems to defy the very concept of solidity. Take asteroid 253 Mathilda, a dark, cratered world visited by the near-Shoemaker spacecraft in 1997. When scientists calculated its mass and volume, they were met with a number that made no sense. Mathilda's density is astonishingly low, less than half that of a typical rocky asteroid. The inescapable conclusion is that this world is not just a loose rubble pile, it is a cosmic void. Up to 50% of Mathilda's volume might be nothing at all, just empty space. It is less a rock and more a collection of boulders and dust held together so loosely that it is mostly gaps, a celestial sponge or a piece of Swiss cheese floating in the dark. This is not a solid body with a few caves. It is a body that is mostly cave, a fragile lattice of touching stones with cavernous chambers between them. Imagine the interior not as a dense core but as a labyrinth. Picture a cutaway diagram. The outer crust is just a thin, fractured shell of compressed rubble. Inside, the structure gives way to a three-dimensional maze. Enormous boulders, some as large as houses, float without touching, held in place by the gentle gravitational pull of their neighbors. Between them are vast, interconnected voids, shadowy chambers that have never seen sunlight, where a stray pebble might tumble silently for minutes before coming to rest. The entire structure might shift and settle with the faintest tremor from a distant impact, a slow, eternal rearrangement in the microgravity dark. This bizarre architecture has profound, practical consequences for our future in space. The fantasy of asteroid mining, where spacecraft land on a solid surface and drill for precious metals, shatters against this reality. Landing on a world like Mathilda would be like trying to anchor a ship to a floating cloud of gravel. Any thrust from landing engines would likely blast a deep crater and send the entire local surface into chaotic motion, potentially burying the spacecraft or triggering a collapse. And drilling would be meaningless, as the drill bit would simply push boulders aside, entering void after void. Even more critically, this changes planetary defense. If a potentially hazardous asteroid headed for Earth were a fragile, high-porosity object like Mathilda, our deflection strategies would need a complete rethink. A kinetic impactor, like the one used in the DART mission, might not simply nudge such an asteroid. It could punch straight through like a bullet through a snowbank, transferring very little momentum and perhaps just dispersing the rubble into a cloud of still dangerous fragments. Or the impact might be absorbed entirely, the energy dissipated as the entire structure compresses and rearranges itself internally, leaving its trajectory barely changed. This forces us to see these worlds not as monoliths but as aggregates where the rules of physics play out in counterintuitive ways. The empty asteroid is a silent reminder that in space, substance can be an illusion, and what looks like a mountain from afar might be, in truth, a haunted house of stone and shadow, held together by nothing more than a whisper of gravity. The fragile, cavernous structure of an asteroid like Mathilda is a testament to the quiet forces that shape them, but the grandest force of all orchestrates their very place in the solar system from a vast distance. This leads us to the strange gravitational symphonies known as orbital resonances. Far from drifting aimlessly, many asteroids are locked in precise, repeating dances with the giant planets, their orbits dictated by the relentless mathematics of gravity. The most stunning example is found with Jupiter, swarming around the gas giant, not in a belt but sharing its orbital path, are two vast clouds of asteroids known as the Trojans. These rocks are trapped in gravitational sweet spots called Lagrange points, specifically the points 60 degrees ahead of and behind Jupiter in its orbit. Here, the combined pull of Jupiter and the Sun creates a stable pocket of space, a cosmic eddy where objects can be captured and held indefinitely. Imagine Jupiter on its marathon journey around the Sun. Leading the charge is one great swarm of Trojans, and trailing behind like a loyal retinue is another, all moving in lockstep with the planet, forever kept at a safe, stable distance. They are prisoners of gravity, but prisoners in a gilded cage, riding the celestial currents in perfect harmony. This gravitational influence also carves out emptiness. Look at a map of the main asteroid belt, and you will notice strange, distinct gaps where almost no asteroids are found. These are the Kirkwood gaps, and they are not accidents of distribution. They occur at specific orbital distances where an asteroid's period, the time it takes to orbit the Sun, forms a simple integer ratio with Jupiter's period. For example, an asteroid in a 3-to-1 resonance with Jupiter would complete exactly 3 orbits for every 1 orbit Jupiter makes. This creates a recurring gravitational nudge. Like pushing a child on a swing at just the right moment, Jupiter's periodic tug, always at the same point in the asteroid's path, adds energy over time. This repeated perturbation doesn't just shift the orbit slightly, it fundamentally destabilizes it, eventually flinging the asteroid out of that resonant zone entirely, either deeper into the inner solar system or outward toward the giant planets. The Kirkwood gaps are therefore not empty because asteroids never formed there, but because Jupiter's gravity has efficiently cleared them out over billions of years, acting as a cosmic janitor with perfect rhythm. To visualize this grand puzzle, picture an animated orbital diagram. Jupiter, a massive sphere, travels along its path. Ahead and behind, 2 shimmering clouds of thousands of dots, the Trojan swarms, move in perfect synchrony. Then the view zooms to the asteroid belt between Mars and Jupiter. The belt appears as a dense, swirling ring of particles, but within it, several sharp, clean bands are conspicuously empty, the Kirkwood gaps. As the animation runs, you can see hypothetical asteroids entering these gaps, their orbits becoming increasingly elliptical and chaotic with each resonant pass of Jupiter, until they are violently ejected from the region. This reveals the asteroid belt not as a random scattering, but as a finely tuned gravitational filter. Every asteroid we see today, from the tiniest grain to the largest protoplanet, is in an orbit that has somehow survived this billion-year-long celestial sorting process. Their positions are a live map of gravitational forces, a permanent record of which orbits are allowed to persist and which are forbidden by the laws of physics. The empty spaces speak just as loudly as the rocks themselves, telling a story of cosmic mechanics written in negative space. If gravity can create such perfect voids and such perfect congregations, what other invisible patterns are etched into the fabric of our solar system? That gravitational sorting in the asteroid belt has a terrifying, tangible consequence for life itself. The most infamous and consequential asteroid in Earth's history is the one that ended the reign of the dinosaurs. 66 million years ago, a mountain from space, now known as the Chicxulub impactor, slammed into what is today the Yucatan Peninsula. From the geological crime scene, scientists have pieced together a portrait of the killer. It was not a metallic bullet or a loose rubble pile, but likely a carbonaceous chondrite, a dark, carbon-rich asteroid roughly 10 kilometers or 6 miles wide. Think of it as a massive, brittle stone, perhaps similar in composition to the dark, primitive asteroids we see today. Its speed was astronomical, striking at an angle of about 60 degrees, which maximized the horror of its effects. The energy released was beyond comprehension, equivalent to billions of atomic bombs detonating at once. The immediate aftermath was pure hell on Earth. At the point of impact, the rock and the target vaporized instantly, creating a fireball that expanded across the continent and ignited global wildfires. The collision excavated a crater over 150 kilometers wide, hurling trillions of tons of vaporized rock, sulfur, and dust high above the atmosphere. Then came the tsunamis, waves hundreds of meters high that scoured coastlines thousands of miles away. But the true killer was what followed. All that ejected material began to rain back down, heating the upper atmosphere until it literally glowed, broiling the surface below. Then, as the finer particles remained aloft, they encircled the entire planet in a thick shroud of dust and sulfate aerosols. Sunlight was blocked for months, perhaps years. Photosynthesis collapsed, global temperatures plummeted in a prolonged impact winter. The food chain, from the smallest plankton to the mightiest tyrannosaur, unraveled. This single asteroid impact directly caused one of the 5 great mass extinctions, clearing the stage for mammals and eventually humans to rise. The search for its exact origin continues today. Astronomers use computer models to run the solar system's clock backward, tracing potential pathways from the asteroid belt to that fateful intersection with Earth. The likely suspect is a family of dark, primitive asteroids in the outer belt, whose orbits can be destabilized by gravitational resonances with Jupiter, sending fragments on a chaotic journey inward. This transforms the bizarre into the deeply personal. That dark, silent rock drifting in the belt was not just a curiosity. It was a loaded gun in a cosmic shooting gallery, and its bullet forever altered the story of our planet. Visualizing this event requires a scale that defies human experience. Imagine an animation, first from space, showing a small, dark speck on a collision course with the brilliant blue and white marble of Earth. The impact is not an explosion, but a planet-wide deformation, a ripple of energy that lights up the hemisphere. Then, from the ground, the sky turns blinding white, then an impossible, roiling red as superheated debris falls, before fading to a permanent, choking gray. The silence after the cataclysm is the silence of a world reset, a direct result of one bizarre rock's journey from the distant belt to our front door. The shadow of that ancient impactor reminds us that not every visitor from the void is a natural relic of the solar system's birth. Sometimes the cosmos sends us an object that makes us question what is natural at all. In November 1991, astronomer James Scotty at the Kitt Peak Observatory spotted something utterly perplexing. Catalogued as 1991 VG, this small object, perhaps only 10 meters across, was following an orbit around the Sun that was eerily similar to Earth's own. Its path was not a wild ellipse from the asteroid belt, but a nearly circular track that brought it periodically close to our planet. That alone was unusual, but the real mystery was in its light. As telescopes tracked it, 1991 VG did not shine with a steady glow. Its brightness flickered and flared with a rapid, dramatic rhythm, doubling and then having an intensity every few minutes. This was the signature of a tumbling object, spinning chaotically end over end, its irregular shape reflecting sunlight in brilliant, strobing flashes as it rotated. In the context of the early space age, a shocking hypothesis briefly flickered to life. Could this be artificial? The timeline was suspicious. Its orbit meant it could have been looping the Sun since the late 1950s or early 60s. Was it a discarded rocket booster from an early lunar mission, perhaps a forgotten piece of the Apollo program, finally spotted on its long journey back to our neighborhood? The idea captured imaginations, suggesting a ghost from our own technological infancy returning home. Scientists, of course, got to work. Further analysis of its path and composition, though limited by its size and distance, strongly suggested a natural origin. The leading theory today paints a different but no less fascinating picture. 1991 VG is likely a fragment that was knocked off the Moon by a major impact, a lunar meteorite set adrift, or perhaps a rare type of asteroid that found itself captured into an Earth-like orbit through complex gravitational interactions. The rapid tumbling is a clue to its violent history, a spin imparted by whatever event launched it on its solitary path. While the artificial origin was relegated to fringe speculation, the episode remains profoundly important. It was a moment of genuine, if fleeting, uncertainty where the line between the natural and the human made universe blurred. It highlighted how our own exploration can litter the cosmos with artifacts that might, one day, be mistaken for asteroids by future generations. More than that, it underscored a humbling truth. Even with our advanced technology, some small, dark objects can behave in ways that momentarily stump us, forcing a double take at the starry sky. Visualize this mystery, a lone, glinting speck tumbling against the backdrop of the Milky Way, its light pulsing like a silent beacon. For a brief moment, we wondered if we were looking at a lost piece of ourselves, only to realize the universe is still perfectly capable of crafting its own enigmatic signals. The line between a cosmic threat and a cosmic opportunity is thinner than we think. After exploring 24 bizarre discoveries, from ghostly magnetic fields to diamonds forged in chaos, we arrive at perhaps the strangest concept of all, a future where these silent wanderers are no longer just objects of study but destinations. The final bizarre find is not something scientists have dug up, but something they are planning to build, a new chapter where humanity turns ancient debris into the foundation of a spacefaring civilization. This vision transforms asteroids from distant curiosities into the most valuable real estate in the solar system. The resources they hold are the keys to unlocking the stars. Water ice, once a shocking discovery, becomes the most precious commodity. In space, water is not just for drinking, it is rocket fuel. When split into hydrogen and oxygen, it becomes the propellant that could power ships from Earth orbit to Mars and beyond. An asteroid rich in ice becomes a cosmic gas station, allowing us to refuel without the colossal cost of hauling every drop from Earth's deep gravity well. Then there are the metals. An asteroid like Psyche, that exposed metallic core, contains iron, nickel, and cobalt in amounts that dwarf terrestrial mines. In the airless, microgravity environment of space, these materials could be processed and used to construct enormous habitats, solar power satellites, or spacecraft, all without ever touching our planet's surface. The technologies proposed to make this happen sound like science fiction, but they are being designed in labs today. Swarms of autonomous robotic miners could land on a rubble pile asteroid, carefully extracting material without destabilizing its fragile structure. Solar concentrators, giant mirrors focusing sunlight, could melt metal right on the surface for collection. For planetary defense or precise resource capture, scientists have even theorized gravity tractors, spacecraft that would hover near an asteroid for years, using their own tiny gravitational pull to gently nudge the larger body onto a new, useful trajectory. This is the ultimate twist in our relationship with these ancient stones. We began by fearing them as agents of extinction, like the Chicxulub impactor. We then marveled at them as scientific puzzles, holding the secrets of our own origins. Now we look ahead to a time when we might gently harness them. The most bizarre thing we will ever find on an asteroid, therefore, might be a human footprint or the glow of a robotic welder against the eternal night. Imagine concept art of that future, not as a distant fantasy, but as a logical extension of every discovery we have made. A spinning, diamond-shaped asteroid like Ryugu is encircled by a delicate web of infrastructure. Reflective processing plants cling to its surface, fed by silent, crawling excavators. In the black sky above, a streamlined tug prepares to depart, its cargo hold full of purified water ice, destined for a waiting depot at the moon. This vision recasts the entire asteroid belt. It is no longer a graveyard of failed planets or a shooting gallery of hazards. It becomes a toolkit, a hardware store stocked with the very materials we need to become a multi-planet species. The final and most profound, bizarre discovery is not in the past, but in our future, the moment we realize that the building blocks for tomorrow were floating beside us all along. From water worlds to metal hearts, from cosmic diamonds to interstellar scouts, the journey through these 25 discoveries reveals a truth we can no longer ignore. Asteroids are not the boring, static rocks of our old textbooks. They are a stunningly diverse gallery of worlds, each with its own dramatic story. They are the exposed cores of shattered planets, the frozen arcs carrying life's blueprints, the tumbling rubble piles reshaping themselves in silence, and the dark, tar-covered relics from the solar system's coldest beginnings. They hold the keys to our past, explaining how our oceans formed and why the dinosaurs vanished. And they offer the promise of our future as the cosmic gas stations and hardware stores that could one day fuel our journey to the stars. Every bizarre find, from the ghostly tales of active asteroids to the faint fossil magnetism locked in ancient stone, forces us to look up with new eyes. The small worlds drifting in our neighborhood are anything but simple. They are dynamic, mysterious, and endlessly surprising. So, which of these bizarre discoveries amazed you the most? Was it the idea of a mountain-sized diamond forged in a collision, or the lonely interstellar visitor tumbling through our system? Let us know in the comments below. If this journey into the unknown captivated you, be sure to like this video and subscribe for more explorations into the greatest space mysteries. The next time you look at the night sky, remember, the real wonders are often not in the brightest stars, but in the quiet, dark spaces between them, where countless strange and silent worlds continue their eternal, mesmerizing dance.